Hi, I'll try to explain about the different types of crystal systems. In the earlier video, I spoke about the types of solids. One is crystalline and amorphous solids. So we also discussed that crystalline solids have one particular arrangement. So the arrangements, when we are seeing them in terms of lattices, so the crystal systems, the lattices are of the following types. So there are 7 crystal systems or the lattices in which the crystalline solids are in general arranged. So these are the primitive types in which different solids can be arranged. So let us see the 7 crystal systems. The first one among them is cubic crystal system. So I have given the diagrams of all the crystal systems so that we can refer them to understand them better. So first type of crystal system is cubic crystal system. So it is similar to a simple cube. In a simple cube we know that all the sides are of equal length. Let the first side be A, let the second side be B, let the third side be C, and A is equal to B equal to C, and all the angles between the sides. Let the angle be alpha between this two sides, let the angle be beta between these two sides, angle be gamma between these two sides. So the angle alpha is equal to beta is equal to gamma. That is what I have tabulated here. So the cubic system has A equal to B equal to C and alpha equal to beta equal to gamma, which is equal to 90 degrees. An example of that is NaCl. So that means when you try to take out an NaCl, the lattice positions are occupied in this manner. That is, all the atoms occupy the lattice positions in the form of a cube. So that is what is called as a crystal system. The second crystal system I want to speak about is tetragonal crystal system. So in the tetragonal crystal system, we have a square at the bottom and the height of the cube is different from the length of the side of the square. That is, if the square is made up of A and B, A is equal to B, but the height of this cube, which is C, is different from A and B, but all the angles are still 90. So if we say A is equal to B but B is not equal to C, and all the angles are still equal to 90. The corresponding examples are here, you can have a look. To make things clear, I'll be using certain props. An example of tetragonal would be this. So if you see, this is side A, this is side B. So it's a regular square. This is a regular square and the height of which is C. So this C is, the height is different from the sides of the square. But as you can see, this angle is 90, this angle is 90, and this angle is 90. All the angles present in this are 90 degrees. So this is an example of a tetragonal system. Next, let us move to orthorhombic system. So in an orthorhombic system, all the side lengths are different. That is, A is different from B and B is different from C, but all angles are still maintained 90. So it looks like an old computer CPU. So I'll also use an example for this. This is an example of orthorhombic crystal system. The common matchbox that we see is an example of orthorhombic crystal system. So in this, if this is A and if this is B, you know A is different from B and the side C is even different from A and B. But all angles are still 90, as you can observe in this. So this is an example of orthorhombic crystal system. Hope this clarifies the point. Next, let us move to hexagonal crystal system. We don't have a typical example for this. That means I cannot show you with a property, but a hexagonal crystal system somewhat looks like this. This is a hexagonal crystal system where you can still view it in the form of a cube. So this is side A. So you can see a hexagon already. The base is also a hexagon, and this is side A, this is side B. The height of the hexagon is side C. If this solid hexagon, the height is C. So this angle is 90. This angle is also 90, but the angle present here, this is gamma, which is equal to 120. That's what I've written here. It's not clear, but gamma is equal to 120. In this I've shaded the cube part of it. So that is a cube in the hexagon. I'll also try to show this. So here I have constructed a hexagon. So in the hexagon, this is the base. So all the sides, this will be the height of the hexagon. So you can say these will be the heights of the hexagon. So inside the hexagon you can still see a cube. So I can arrange the cube like this. So this would be the height of the hexagon, what I'm showing. What I'm showing is the height of the hexagon. I hope that's visible. So still there's a cube inside the hexagon. So we are speaking about different angles here. So if this is A, if this is B, this would be C. That would be C. And we can also check the angles between them. Now if we check, this angle is 90. This angle is also 90. But this angle, the angle between these two sides that you can see, is 120. I'll try to draw it here. So this internal angle is 120. That's a 120 degree angle. Whereas the angle between this one and this one is 90. The angle between this side and this side is also 90. So I'll label them. Let this be side A, let this be side B. This matchstick, or let this be side C. So angle between A and C is 90, angle between B and C is 90, but angle between A and B is 120. So that's the hexagonal crystal system. Let's move back to the next crystal system, which is rhombohedral crystal system. Okay, first let's speak about monoclinic, then we'll move to the monoclinic system can be explained in terms of A, B and C, where all the values of A, B and C are different, but this angle is 90, this angle is 90, but the other angle that is left out is not 90. How do we show it? So we can explain it by saying that if we are using shearing stress on top of a orthorhombic system, it would be monoclinic system. Shearing stress means if I'm pushing out the top layer. Let me take an example for that. I'm using a property again. So let me take this matchbox. So in this, let us say there is one side A, the other side is B, and the other side is C. All the three sides are different, and when I try to push the matchbox like this, so when I apply stress on the topmost layer, that is shearing stress. That is, this layer is tilted. That is shearing stress. Now if I try to look at the angles in this, what about this angle? The angle that is visible between these two, this angle is definitely not 90. So let us say this is side A, this is side B. The angle between A and B is not 90. But let us tilt it over like this. This is side C. So this angle is remaining as it is as 90, and this angle is remaining as it is as 90. See, this is still perpendicular, this is still perpendicular. The only angle that is changing is this angle. So that angle is not 90. So while showing a monoclinic, I'll say all the sides A is not equal to B, B is not equal to C. Two angles are equal to 90, one angle is not equal to 90. So that is an example of monoclinic shape. Okay, let me try making this into a rhombohedral one. I'm just trying. Let's take out a second on this. Let me cut it into a regular cube first. Okay. Now, this is not a square. So this angle would be different. This is a rhombus. This angle is different. This angle is different. So when this is bent in a direction, that is, this whole thing is bent in this direction. It's bent. What I'm trying to do is, okay, I have to cut this out also. So this is, let all the side lengths be equal, and when I'm trying to, now this is a rhombus. I think you can see the similarity between this and this. Now when instead of this being in a straight line, it is bent. So this angle is different, this angle is different, and this angle is different. All the angles are different. None of the angle is 90 here. So all the angles are different, and this whole thing has to shift in one direction, so that this angle that you see will also shift away from 90. So this one also should shift in this direction. So these two are right now in a straight line. If this shifts in this direction, that is, the whole of this shifts in this direction, if I apply shearing stress to this on this direction, then this angle would also change from 90. So all the three angles are different from 90, but all the three side lengths are equal. So that would be okay. This explains that better. So you can see I have applied shearing stress in that way, but these two lines that you see should shift in this direction. That is, they are like this right now, they should shift in this direction, so that this angle also becomes more than 90. So this base remains intact. This side tilts to the right side, this side tilts to the right side, then it would be rhombohedral. This was the most difficult one to make. Okay, the last one is triclinic, in which all the three sides are different. As you can see, A is different from B, B is different from C, and when you push it, it is nothing but similar to this. When you push it, all the angles would also be different. None of the angle would be equal to 90. The same push that I did on rhombohedral, you would do on triclinic also. None of the angle would be 90. So in reality, while preparing for the exam, you just need to know about the values of ABC with respect to the angles. That's the only data that you would be requiring. Just I've tried to explain with different properties so that you can understand, you can imagine them better with a property. So that is about the 7 crystal systems. Now let us also see about secondary lattices, which are the positions of the atoms explained in a lattice. So when I take a simple cubic crystal system, so I can place the position of the atoms at different places. When I place the position of atoms at all the corners, then it would be called a simple cubic lattice. This is a simple cubic lattice. Now the second type is face centered cubic lattice, which is abbreviated as FCC. In this, apart from the corners, so these are the corners, apart from the corners, on the center of every face, this is a face, on the center of the face there is an atom. As you know, a cube has 6 faces, there will be 6 atoms on all the 6 faces. So that is face centered lattice system. The next one is body centered cubic system, where on the center, in the center of the whole cube, there is one atom apart from the corners. And the last one is end centered. So apart from the corners, on this end and on this end, in the center of these two ends of the cube, you have 2 atoms. So that is end centered lattice. So in total we have 7 crystal systems, as you can see, for 7 crystal systems which we have just discussed. Along with that, 4 lattices.